folks. In this next section, we're still learning how to solve systems of linear equations, but this time we're going to use a different strategy. Last time we learned graphing. This time we're learning how to use substitution to solve these systems. And substitution, this isn't a math definition, this is just a regular vocab definition. Just means replacing one thing with another. So if you think about a substitute teacher, you're replacing a temporary substitute for your normal regular teacher. You're replacing your regular teacher with a substitute for a day or so. And so what we're going to do here is we're going to actually replace a variable, replace x or replace y with an expression that means the same thing. So let's look at how this works. I have a system of equations here. Y equals negative 2x minus 9 and 6x minus 5y equals negative 19. And what I want to do, I know that y equals negative 2x minus 9. Therefore, any place I see a y in the equation, I can actually replace it with that equivalent expression, negative 2x minus 9. So let me do that. I'm going to rewrite this 6x minus 5y equals negative 19 equation where I replace the y. I'm going to write 6x minus 5. I'm going to leave myself plenty of space here, equals negative 19. I'm going to replace that y with this expression that means the same thing as y, the negative 2x minus 9. Negative 2x minus 9. This equation means the exact same thing as the original equation written above it. These two equations are totally equivalent. I've just replaced the y with an equivalent expression, negative 2x minus 9. We now solve for the remaining variable. Y has now disappeared because we replaced it with an expression that contains x. And so now I only have x's in the equation and I can solve for x. How do I do that? First step is simplify, and then which includes getting rid of any parentheses, combining any like terms, and then I use reverse PEMDAS to solve for x. So I've got some parentheses here, so I'm going to do the distributive property like this. I've got 6x, negative 5 times negative 2x is positive 10x. Negative 5 times negative 9 is positive 45. And all of that still equals negative 19. That side stays unchanged. We've gotten rid of the parentheses, but I still have some like terms here that can be combined. So I've got 16x from combining those two together, plus 45 equals negative 19. And now that I've simplified the left side of the equation as much as possible, I can now use the reverse PEMDAS order. I'm going to do addition subtraction first. And right now, to get x by itself, I need to get rid of this 45 that's being added to it. So I'm going to subtract it away. And now I've got 16x equals negative 64. Again, the goal is to get x by itself, so I need to get rid of that 16. The 16 is multiplying the x, so to get rid of it, I'm going to divide that away. Divide both sides by 16, and I get that x equals negative 4. Now, I'm not done with this problem because I'm supposed to solve the system by substitution. I'm trying to find the point, the ordered pair where both of these equations are true. So right now I know the x coordinate. I know the x coordinate is negative 4, but I don't know the y coordinate. So my answer here is incomplete. I need to know the y coordinate. How do I figure out the y coordinate? I take that x value and I substitute it into one of the original equations. And it's important to go back to an original equation, not a modified equation, so that you're sure you're testing those original equations. So I'm going to use this -4 value of x in one of the equations. The top equation looks easier to me than the bottom equation in terms of solving for y, because it already has y all by itself on one side of the equation. So let me do this in a new color just to keep track of where we are. Y equals -2x minus 9, but I know that my actual value for x is -4. So I'm going to plug -4 in here, and then I'll subtract 9. Please be careful when you substitute values. -2x, that's a multiplication problem, -2 times x. So when I plug my -4 in here, I write the -4 in parentheses so that I remember it is a multiplication problem. I don't want to accidentally subtract 4. I want to multiply by -4. All right, so looking at this structure, -2 times -4 is 8. And then I subtract 9, so I get y equals -1. So I'll plug -1 in here, and now I have a complete answer, a complete ordered pair. I think that this is the solution to this system of equations. Now, I don't have to just think it, I can prove it. I can demonstrate that this is the correct solution by going back and checking the solution in each of the original equations. Okay, so this extra step doesn't take very long, but it's important. It's an important check to make sure that I actually did all my math correctly. So I go back to one of the original equations, y equals -2x minus 9. I plug in this value for x. I plug in this value for y. So my y is -1. My x value is -4. And when I plug this in, I see that -1 is in fact the value that I get when I have 8 minus 9. So that checks out. Then checking the other equation, 6x minus 5y equals -19. My x value is -4. Remember, that's a multiplication problem, not subtraction. Minus 5 times -1. That's a multiplication problem. Here, this is subtraction. This is a subtraction sign. This is a subtraction sign. But 6 times -4 is multiplication. 5 times -1 is multiplication. This all equals -19. 6 times -4 is -24. -5 times -1 is +5. So now it's become an addition problem. And that does in fact equal -19. So I have now confirmed that this is the ordered pair that is the solution to this system of equations. Let's try another example. And as always, if you can pause the video and solve it ahead of me and then check your work, that's even better. I'm going to show you two different ways to do this problem. Usually the first way is more obvious to students, but there is a slight shortcut that I'll show you at the end. Solve the system of equation by substitution. Notice that neither equation has any one variable already solved for in one of the equations. I don't have x equals something or y equals something all by itself on one side of the equation. So I'm going to want to maybe rearrange one of these equations to solve for a variable. Now here, when I look at x here, I'm multiplying by a number and I'm adding something to it. When I look at y, I'm multiplying by a number and adding something to it. This second equation looks a little harder to rearrange, but this first equation looks very simple to rearrange. Y doesn't have anything multiplying it. I just need to subtract 8 from both sides of the equation, and then I'll have y all by itself. So let's do that. 3x equals y plus 8. If I subtract 8 from both sides of the equation, I get that y equals 3x minus 8. I have y all by itself on one side of the equation. So I know that y can be replaced by this expression, 3x minus 8. So I can go to this second equation. Be careful that you don't go back to the original equation that you rearranged. That will get you an answer that's just always true. It won't be helpful. You won't actually be able to solve for y. You'll just get something like 0 equals 0 at the end. So make sure you go to the other equation now, and I'm going to find wherever y appears in that equation, and I'm going to replace it with this 3x minus 8y. So let me write this down. 3x plus 2y equals -1, but I'm going to replace that y with this expression, 3x minus 8. Remember, 3x minus 8 means the same thing as y, so these are equivalent equations. Now, x, you can see x is the only variable left in this equation. So now I want to solve this equation for x to get the x value of my solution. So I'm going to do the distributive property. First, I'm going to simplify what I can on the left-hand side, and then I'll solve for x. So did the distributive property here, let's see, my 3x stays as 3x, but when I get to this distributive property, 2 times 3x is 6x, 2 times -8 is -16, and that all equals -1. I haven't done anything to the right side of the equation yet. I'm not quite done simplifying yet because I still have like terms to combine. So I've got 3x plus 6x is 9x, minus 16 is -1. And now I've simplified the left side as much as I can. So I'm going to solve for x to get x all by itself. We do this in reverse PEMDAS order. When you're solving for a variable, you go in reverse PEMDAS order. So I'm going to take care of any addition, subtraction I see first. And this 16 is being added to the, or subtracted from the x. So I'm going to get rid of that 16 by doing the opposite, by adding it. And then I have 9x equals positive 15. And the goal is to get x by itself. So to get rid of that 9 that's attached to x, I'm going to divide it away. And I'm going to have that x equals, we can simplify that fraction so that it's 5/3. I know my x value in the equation, but I don't know my y value. So I don't have an answer yet. Remember, the answer, if I'm trying to solve a system of equations, I need to have an ordered pair with an x value and a y value, and I only know the x value so far. I don't know the y value yet. So let's do that next part. Let's find the y value. How do I get the y value? By taking this x value and replacing it in one of the original equations. So when I look at the original equations, I think this equation maybe looks simpler. Seems to have less going on. So I'm going to write that equation down. And then I'm going to replace that x with the value that we determined, that 5/3 fraction, equals y plus 8. Remember, it is important to go back to your original equation, not your modified equation, not the 3x minus 8 equals y. We do this because if you made a mistake in getting that modified equation, your solution might work for that modified equation, but if you had made a mistake, it will work there, but not for the original equation. So always go back to your original equation to make sure that you didn't make a mistake somewhere along the way. All right. To solve for y, we want to get y all by itself, but remember to simplify first. I've got a multiplication problem here that I can take care of. 3 times 5/3 is just 5. And we can now subtract 8 from both sides of the equation to get y all by itself, and y equals -3. So now I have a complete, sorry, I have a complete ordered pair. This is the solution to this system of equations, but it's always wise to go back and check to make sure that it is in fact a solution by plugging those answers back into both of the original equations, that x value and that y value. You can, you don't have to write it down on paper necessarily, just doing a quick calculator check will do. I'm going to write it down here just so that you can see what it is I'm doing. I'm just checking the solution, check solution. I am going to plug that x and y value into the equation. So 3x equals y plus 8. I'm going to plug in 5/3 where the x value is, because that's what my solution says here. And y is -3. And I'm going to add 8 to that. So on this side, when I do the multiplication, 3 times 5/3 is 5. And -3 plus 8 is 5. So that checks out. And I can test the other equation. 3x plus 2y equals -1. Well, x was that 5/3 fraction. And 2y, let's see, y is -3. And that all equals -1. When I do the multiplication here, 3 times 5/3 is 5. Plus -5, I'm sorry, plus -6, because -2 times -3 is -6, equals -1. That also checks out. -1 equals -1. So I've demonstrated that this is in fact the solution to this system of equations. Now, I told you at the start of the problem that there was a slightly simpler way to approach this example. I'm just going to erase some of my stray marks here. The slightly shorter way to do this problem happened at the very first step. At the very first step, we said that we needed to solve this equation for y, and then we rewrote the equation for y over here. There is a simpler way because you don't actually have to solve for just a variable. You can solve for an expression instead. Notice that the top equation has a 3x in it, and the bottom equation also has a 3x in it. So what I'm going to do is I'm going to write this second equation over here. And remember, I'm going to take this whole 3x term and replace it with that y plus 8. So I'm going to write y plus 8 plus 2y equals -1. Again, where did that y plus 8 come from? 3x is the same as y plus 8, so I just replaced that 3x with the y plus 8. What do I have on the left side of the equation? I've got a couple of like terms here that can be combined. Y plus 2y is 3y. And then still add the 8, don't lose that 8, equals -1. I can now subtract 9 from both sides of the equation. I'm sorry, subtract 8 from both sides of the equation. I was getting ahead of myself. It equals -9. So I get 3y equals -9. To get y by itself, divide both sides by 3. And I have y equals -3, which is the same y value that we discovered before. So it's just a small shortcut. We kind of cut out these steps here written in red that we did at first by substituting an expression in an equation instead of having to solve for the variable first. Let's look at a real-world problem. The value of looking at this particular real-world problem, I took this straight out of the textbook. Normally, I would not have chosen to solve this by substitution. because we've got some pretty big numbers here, and it's a little bit awkward. I would probably preferentially do this one by graphing, but you don't always have a graphing calculator, and it's good practice to learn how to deal with these real world problems. So we're going to go ahead and look at it. Remember, we talked about this a bit in chapter 1, 2, 3, several chapters, that standard form works well for linear equations when you've got two different items with each with their own rate, and you know the total. Slope-intercept form works well for linear equations when problems have just one rate and a starting value. So as we kind of read this problem, we'll kind of decide which form works best for this situation. On opening night, a comedy club sells 68 adult tickets and 136 student tickets for a total of $1,088. And on the second night, the club sells 79 adult tickets, 140 student tickets for a total of $1,183. So I kind of have these two nights. I'm going to write two equations, one for each night. And I have, we want to know the price of each type of ticket. So let's define our variables so we know what they are. I'm going to say X is the price of the adult tickets here. And I'm going to say Y is the price of the student tickets. Okay. So I'm missing two rates in this equation: the price of adult tickets, the price per ticket for an adult, and the price per ticket for a student. Since I have two rates, the standard form is going to work well here. I'm going to have some number times x plus some number times y equals c. Here I know the number of tickets of each type being sold. So if I know the number of adult tickets sold and I multiply that times the price, which I don't know, but I've given it a variable, so I'm going to use x. And then I add that to the number of student tickets sold. Sorry, that's 136 times that student ticket price, which is y. I don't know the number, but I've given it a variable. That all together is going to equal that total money made of $1,088. We can set up a similar equation for the second night, which is 79 adult tickets plus 140 student tickets equals 1,183. So here are my two equations. I now have a system of equations. I want to find the one solution where both of these equations are true to get me that x value, the price of adult tickets, and the y value, the price of student tickets. Let's rearrange this first equation first. 68x plus 136y equals 1088. I chose this equation just because it has smaller numbers in it. I want to solve for a variable so that I can use that variable, plug it in to the other equation to solve for the other variable. So in this example, I'm going to go ahead and solve for y. I'm going to get y all by itself. It doesn't really matter. One isn't obviously more easy than the other for this particular case. They're both big numbers. So let's solve for y. To solve for y, first of all, there's no simplifying that needs to be done, no parentheses, no like terms that can be combined. So instead, I'm just doing reverse PEMDAS order. I'm going to get rid of anything that's being added to the y. So I'm going to subtract 68x from both sides. So now I have 136y equals 1,088 minus 68x. And now to get y all by itself, I need to divide by 136, divide by 136, and that gives me y equals, we talked about this in the previous video, how important it is when you divide a multiplication or division problem when you divide an addition or subtraction problem by a number, to use the distributive property, be sure you divide all parts of the addition or subtraction problem by your number. 1088 divided by 136 is 8. And negative 68x divided by 136 is negative 0.5x. So I now have a pretty simple equation, actually. It's simplified down into much nicer numbers, simple values that I can then plug into my second equation. Remember, don't plug this expression back into the equation that you got it from, because then you'll get just a statement that's always true, like 5 equals 5. All right, let's take this and plug it back into the second equation. 79x plus 140y equals 1183. But I'm going to take my y and replace it with this expression, 8 minus 0.5x. So the 79x doesn't change. It's the y that changes. So I'm replacing that y with this 8 minus 0.5x. And that's going to equal 1183. This equation only has x's in it. So I can solve for x. We should simplify first. So I'm going to do the distributive property here. The 79x hasn't changed. I just leave it as 79x. But here I have 140 times 8, and that's 1,120. I have 140 times 0.5x, which, or negative 0.5x, which is negative 70x. And that's going to equal 1183. The next step here is I've got like terms. 79x minus 70x is just 9x, but there's still a 1,120 here, and the right side of the equation is still 1,183. I now have simplified as much as I can, so now my goal is to get x all by itself. We're going to go in reverse PEMDAS order. So I'm going to get rid of anything that's being added or subtracted from x first. 1,120 is being added to x. I'm going to subtract it from both sides of the equation. And we're going to get 9x equals, that works out to be 63. And then to get x all by itself, it's being multiplied by 9. So I'm going to divide that 9 away. And I have x equals 7. We've already done a lot of work, but we're not actually done answering the question yet. I now know the x coordinate of my ordered pair, that's going to be the solution to this set of equations, is 7. But I don't know what the y coordinate is yet. So we have another step. I need to take this x value and plug it into either of the two original equations to get a y value. So let's do that next step. Again, I'm going to choose the top equation just because the numbers are slightly smaller. 68x plus 136y equals 1088. And I am going to substitute the letter x with the number 7. Still equals 1088. When I do the number 68 times 7, that works out to be 476. I still have 136y, which is 1088 still. And now to get y all by itself on one side of the equation, I need to do reverse PEMDAS. I'm going to get rid of that 476 by subtraction. 136y equals 612. And to get y all by itself, I'm going to get rid of the 136 by division because that's the opposite of multiplication. And I get as my final y value 4.5. So I can now complete my ordered pair. 4.5 is the correct y value. Now remember, y in this case, going back up to the original problem, we said that y was the price of student tickets. Price of student tickets. And the other value, 7, that was the price of adult tickets. We've now solved the problem. We have an ordered pair that is a solution to the system of equations, and we were able to figure out the price of the tickets accordingly. Of course, to be 100% positive that we've done everything correctly, we should plug those values, that ordered pair, the x value and the y value, into each of the original equations to check to make sure our solution checks out. The solution does check out. So I leave that to you to confirm to yourself. But otherwise, we've answered this question. I hope this helped.